Hello, good morning to everybody. We'll start with the industry section 2 about micro hydro energy recovery and system control towards smart water grids. But first of all, I would like to thank the organization of this event. It is a not common event. Why? Because we invited also some external audience to this conference. I would like to thank the organization, the Portuguese part and the English part of WatefCon18 by this invitation of these experts, all of these experts, and some additional experts in the audience too, to have been able to put together these specialists in this field, the field of energy recoverable and smart water grids, to raise their knowledge, to bring their experience. It's very interesting to show here the main advantage of this implementation of microhydro towards a more efficiently and sustainable management related to water energy nexus for a best future smart water grids. Oops. What can I put? Our students have the best support that we have. Okay. So, in this presentation, we'll give you an overview about the REDAWN that we intend to implement microhydro solutions. We'll give you also a municipal overview of opportunities and challenge in water networks. We'll talk about system control, concerns about leakage detection, flow and pressure variation. We'll present some environmental and regulatory opportunities and constraints, some case studies, and at the final section we'll have a question and answer part and some discussion. Be careful with the time, okay? Do not exceed your time. We have 15 minutes or less, okay? Well, and at the end I will make a summary of the session with some closing remarks and what happens next, okay? Well, here we'll have our experts, and I pass the word to Dr. John Gallagher, who comes from Trinity College of Dublin. He's assistant professor in environmental and system modeling, and it is also a member of REDAWN project. Dr. John Gallagher will talk about, will give you an overview about the REDAWN project. REDAWN project, we have here some information about this. Thank you.
Thank you, Helena, and good morning, everyone. Thank you for coming along again this morning. Yesterday, for any of you that was here for the different WatefCon committees, the Water Energy Nexus is what I was representing at the time. This is a core part of what that committee is working on. I'm just going to skip out here into my presentation. Excuse me for a second. So while I'm waiting for the presentation to be found, the REDAWN project is a project that came about in 2017 through a consortium of researchers and small and medium enterprises to enhance the potential of energy recovery using something called a pump as turbine. So the project is 1 year into its 3-year life. And I'm going to give you a short overview of what we are planning to do and what we have achieved so far in the 3 years. So, REDAWN, as every European project has an acronym, it stands for Reducing the Energy Dependency in Atlantic Area Water Networks. It consists of 15 partners. Some of the logos are represented below. Universities, small and medium enterprises, small businesses, water companies, and also potential installers of this in the industry sector. It consists of partners from 5 different countries, and the objective, one of the key objectives, is to demonstrate the technology in pilots, a very core part of what we're trying to achieve. So for those of you who may not really maybe be dealing with water networks, there's many opportunities for energy recovery, and I thought I would provide just 2 short, quick examples of these opportunities. 1 in water supply networks, 2 in irrigation networks. But our project is also looking at wastewater flows and industry consumption and industry demands and water provision as well. So in water supply networks, an example of a project that has been undertaken in this area and undertaken an initial feasibility of the energy recovery, something I was involved in 5 years ago now. We explored Ireland and Wales as an example of 2 small pieces of the EU, and we identified 80 feasible sites that had the potential to recover 20 gigawatt hours of energy, just in the water networks where there was just too much pressure being dissipated. And that had the potential to save 2.5 million euro in that small pocket of Europe. And obviously there is associated environmental benefits of recovering that energy, and that equated to about 10,000 tons of CO2 per annum for the water companies. Also, I didn't put the figure, but those figures equate to about 2% of the required energy of the provision of water. And with the increasing prices of electricity, increasing prices of water, the opportunities for the water sector to adopt this technology is something that is very, very attractive. However, and I will come to this in a moment, there are still many barriers that we need to overcome. Irrigation networks are another example of opportunities where we can recover energy. Again, in parts of Spain and here in Portugal, there's irrigation networks that are under pressure, literally in a pipe. And from what we have identified at this early stage of the project, that there's opportunities for 43 installations of these small little turbines, these pump as turbines, generating 1,000 kilowatts per year. Again, energy that is simply lost without consideration of the optimized energy efficiency of a network. And so what we aim to do as part of this project is go beyond these pockets of Ireland and Wales and parts of Spain and Portugal, is to replicate how we've assessed the feasibility, to go and examine the potential in our area, the Atlantic area that is represented by our project, but able to assess Europe and beyond in the future. So a very brief explanation of how micro hydropower in water networks works. You simply have a water transmission network and a water distribution network. And within that, you have various points where there is too much pressure. And in these locations, you typically have forms of valves to release that pressure. What we explore is the opportunity to replace those with turbines. So instead of completely dissipating the energy, you recover that energy. Now, why is this not already just happening around the world, you wonder? It seems quite simple in some ways, and the reality is there's many barriers. Turbines are quite traditionally an expensive component to recover energy. So what there is a need for is a low-cost form of a turbine. Really, no one has assessed the market potential on a large scale beyond 1-2 countries, or a region of the countries in some cases. There is a need for policy and regulations. There is a need to associate the environmental benefits and the social benefits that can be translated through economic savings and environmental savings. And for us, a key part of our project is a need for pilot projects to demonstrate the technology in action, to be a kind of final hurdle to persuade practitioners, explain to technical experts how this technology can work, and to water companies. So the aim of the project is simply encapsulated in this: to foster the adoption of hydropower energy recovery technology in built water networks. We hope to address institutional, social, and technological environments. I'm from a civil engineering background, so really I feel more comfortable in the technological domain, if you will. But it's important to this project to address the 3 different core areas. And I think our speaker before dinner last night mentioned governance, and that's a hugely important element of what we need to deliver, ensuring that this technology is not just limited to physical demonstration and being technologically great. So for those of you who are not familiar with the Atlantic area, it's an Interreg funded region in Europe, part funded through the European Regional Development Fund, and consists of parts of the island of Ireland, the west coast of the UK, parts of France, western France, northern Spain, and the Iberian Peninsula. And so we want to look at the resources, what potential there is in these areas in the different sectors, look at what type of off-the-shelf technology can be taken, and look at what is this recovery potential. However, with most research projects, the availability of data to assess this potential is quite the challenge. But that's key to us having industry partners, water companies as part of our central to our delivery of demonstration sites to assess this correctly. And so this pump-as turbine essentially is a pump taken off a shelf and operated in reverse. We had some of our team present some aspects of the project yesterday. I'm sure the presentations will be available to you at the end of the conference. But it provides a low-cost alternative. It does have a slightly lower efficiency to a traditional turbine. The performance, however, is still not fully captured, and that's an element of our project. And it doesn't quite allow complete regulation of flow. But there's huge potential for it to work in parallel with existing control valves and allow for extra control to mitigate against leakage, etc. 2 minutes. In addition, the policy and institutional support tools is a key part of this project. So with the technology being developed by our academic engineering partners, we also have key partners delivering an understanding how water companies work throughout Europe, how governance works across Europe, and how we can implement this in different parts of the EU. And obviously, we're delivering that message that it has environmental benefits, both for customers and businesses. As I mentioned, our pilot demonstrations, which will be in operation over the coming 12 months, and for those of you who are interested in maybe specific sectors, whether it's irrigation, the process industry, or wastewater, through the REDAWN website, you can keep track in our newsletter about how these are being developed and events that we will hold around those so that you can be informed by these physical sites and the technology in place. And through those pilots, we will develop the guidelines and support tools that are necessary to expand this. So just to conclude, pumps as turbines in water networks, it's an area that has had huge interest in the last number of years. The graph on the right shows you how scientific publications have been growing exponentially in the last particularly 5 to 6 years. And so we know a lot more about the technology, and now this project aims to deliver a much broader perspective to allow REDAWN to succeed, and to through developing the guidelines, through understanding policy, and to delivering a technology that has the potential to truly make the water supply network low carbon and energy efficient. So I'm going to conclude with that. Thank you very much for your attention. Our project REDAWN will have 2 more years of activity, and our demonstrations will be a key part of that, and I welcome anyone that is interested to stay connected with us and find out more. Thank you very much.
Okay, next speakers are engineers Rui Silva Santos and Miguel Zilhão, part from IST, another part from redes de sistemas de saneamento. The presentation will be in Portuguese. Who wants to follow this presentation can catch the automatic translator, okay? The devices. Okay, Engenheiro Rui Silva Santos is the CEO of Redes e Sistemas de Saneamento. This is his own company, and Miguel Zilhão is a fellow from IST and a collaborator from this company. Okay, you can start? Yeah.
It's the computer. Let's.
We haven't recovered enough energy to have money to buy good enough computers. Good morning, everyone. Our presentation will be bilingual. I speak in Portuguese, and Miguel has a lot of culture and intelligence. He will be speaking in English, not me. Our presentation is on the part of induction and distribution of water grids, in which we will focus on the resolution of the hydraulic problem, and then only see the opportunity of energy recovery. So we will center on the possibility of, after having solved the hydraulic part, if we can recover that energy or not. First, just to frame this, as you all know, and people from municipalities who deal with this daily, money is less and less. It's more and more expensive. We have a problem of water resources. We have a problem of climate changes, and by the looks of it, humanity is not able to preserve its planet. But one thing that it can preserve is chauvinism. We should preserve that less, and the planet more. But let's move on. The population is growing. It's another factor that is putting pressure on all water resources, and infrastructures are worse and worse. So we have a scenario in which the whole planet is in a problematic situation, but some people don't believe so. Nevertheless, we should remove Mr. Trump from this scenario, and we have a planet that we must take care of, and this that we're talking of is part of this aspect of taking care. Our presentation, we focused, as I said earlier, in trying to solve the problem, because mending doesn't work. It only works in the short term. We don't have long-term solutions. If we continue mending, we will mend here and there, we will grow older and nothing will happen, so we are playing games over here, but our goal is to solve the problem. We don't have to shout. The solution of water problems solves a set of problems, a problem regarding leakage. We have questions to system control, and Margarida Pignon will be talking about that aspect later on. A global management of the grids, and then we'll hear about that later on with Pedro Perdigão, and the way of having more energy efficiency and being able to recover it. We'll talk about it, and the KSB on the physical systems that in technical Portuguese we call them the apparatometers. With this, we'll be able to have a better environment, better economy, and a better service for the population by being efficient in the management of our water. So we will no longer be crying, we will be happier, and we need to seek long-term solutions that will work well. And to remind ourselves, as we see, we have no plan B regarding our planet. We only have this one, and it's this one that we have to live with. This is a big, long sentence made by two philosophers, the two of us, as you could easily deduce. So one of these sentences I think are important. This one, we can only build a long-term, we cannot build a long-term future if we think in the short term. Regarding leakage in Portugal, the average amount is about 30%. In other words, 30% of the water coming out of our reservoirs is not charged. So we're talking about commercial losses. The greatest component is real and physical component, which is in red over here, on which we'll be focusing, because that is where we have the main water problem. We have a multiplicity of hydraulic errors and situations that all of us, mainly the people from municipalities, know very well, and we need to solve this urgently. In terms of the hydraulic balance, what we are focusing on is real losses, in other words, leakages, and by solving that problem, we will solve in one batch. We will decrease our leakages, we will decrease the uncharged water, we have a more efficient use of energy, and we will have an energy recovery, and once again, by being more efficient. Let me just draw your attention to one of these things, these statistics of 30%. Let me call your attention to the fact that we have several statistical indices to represent a specific problem. The question is, by making this statistics, it means that the places with a higher consumption have percentages that are lower because they have higher consumption. So this comes into the global pie. So statistics can be fallible. We have to see this case by case with the lower consumption as well. It's always harmed in these statistics. And as we see up here, statistics are like bikinis. They show a lot, but not everything. So we need to be careful when we use statistics. The four large components of real losses are pressure management, in which in a specific grid, by decreasing pressure, then real losses decrease linearly. We need to prevent this. In the grid control, we have to know what we have and the speed with which we detect and repair our grid. Regarding the pressure part, we have the possibility or not of energy recovery. In other words, if possible, yes, no problem. If it's not economically feasible, let's take a look at something else. And as we'll see over here, we have several technologies, two of which will be presented right after. So, we have to overcome these barriers that we've heard previously to be able to have a better future. We have a whole set of barriers in the technical, economic, etc. In the technical part, usually we have two big problems, which is the question of the information that is available and human resources to be able to solve the problems. With each in one of them, we also have a whole set of problems. For example, in the municipalities, we have questions related to staff, of not having availability, each person has to resort to several fields, and the information that is available is usually scarce. We need to look for it, etc., etc. Here in Portugal, we have an additional problem of fatalism. It's been like this. It'll always be like this. It'll never change. Yesterday, you had a session with suits, but you didn't see a verse with fado songs. But being fatalist. Only in death and taxes, as our friend Benjamin says. So in this area, it's no use being a fatalist. We need to move on. Here, in this presentation, we are focusing on these two sides of this equation of water. In other words, the transmission that we will use as a supply over here and distribution. In our daily work, we find a whole set of problems in which we have to have reservoir control in situations of transmission or managing pressures in a grid. We need to change the functions. We have to solve the hydraulic problem. In Cascais, in which it was our friend Pedro over there, that we did in São João de Estoril, an area in which we lowered the pressure from 5.5 to 4. What happened was, as we see over here, the flow at night decreased substantially to about half, so leakages also went to about half. Leakages here in blue also decreased at the time, and the data that our friend Pedro gave us were at 0. At the time, I don't know what happened. He doesn't know either, because he changed jobs. An example that we are working on at the moment is with the municipality of Santa Cruz. We have Engineer Gustavo, the head engineer of that municipality, in which we have reservoirs from 1,111 up to 0, because we have reached the sea. So we have a great potential here. Just a small example here in this area. And not all reservoirs from the municipality itself, but in which we have a superior reservoir that supplies two inferior ones, in which the dark blue one can only be supplied when the lower level reservoir is full. In other words, we have the possibility of solving the problem with a control upstream of the intermediate reservoir to supply both of them and simultaneously being able to recover that energy. In other words, place a good hydraulic functioning, and then after that we can recover energy. In the same municipality, we studied a pilot area in which after all modulation, etc., in the existing situation, there were very few levels of pressure. In red, the main level of a reservoir at 180 level, almost up to sea level. So we have an enormous energy potential. By changing the system, we divided this into energy levels, so we also have a potential of energy recovery. But the focus is solving the hydraulic problem, and then we can or not recover energy. So we need to take advantage of these opportunities to be able to solve the problem and simultaneously, in inverted commas, make money with it, with that energy recovery. I'm going to pass to Miguel, who will show that we are bilingual.
Good morning, everyone. As Engineer Rui said, the main focus must be to fix the hydraulical problems within the water network. Only then should we assess the feasibility of energy recovery. In order to do that, we need to know where, how, and to do an analysis, a study of the potential of the energy recovery. So where we have this kind of technology can be implemented, as it was referred, in water distribution systems or water supply systems or water transmissions. Of course, the first one, you have more restrictions such as pressure restriction, where you have to ensure the quality for the consumers. You have the total consumption is divided by the network, and you have variables such as consumer demand that increase the complexity within the system. In the water supply system, however, you have less pressure restrictions, and you can terminate all of the flow of the consumption, and you actually would require a pressure control. So with a control valve which Margarida can explain better, or why not a micro hydropower technology? So first we need to set goals in order to achieve our reality and to try to implement this technology. But how can we do that? In water distribution systems, for example, you have two regulation modes. The first one, a non-regulation mode, where you would require the flow meter and a bypass with a flow control valve in order to ensure the minimum pressure in the network. And you would have to have in downstream a pressure reduction valve to ensure that the maximum pressure within the network is not exceeded. In this regulation mode, you would use the nominal speed of the machine. Whereas in the electric regulation mode, you would have a variable speed drive that would allow you to fix an optimal rotational speed or to use a variable rotational speed according to the input flow rate within the machine in order to harness more energy. In a water supply system, since the flow is constant or zero, you wouldn't require that many equipments, but you could still use both regulation modes, where the electrical one, it would be more optimal to use a fixed rotational speed. In order to, and again, it's important, as Dr. said, to try to combine engineering with science and all these disciplines. In order to explain you how important is this analysis, I'll give you an example in Madeira, in the municipality of Funchal. We did a study there in a pilot zone, where in order to fix the grid, we had to implement 50 pressure reduction valves. And out of these 50, only 10 of them had the estimated potential to actually harness good amount of energy. And after some detailed study, only 2 to 3 of them actually had a good payback period. So we need to study this first. As you can see in this graph, these show the 4 PRV location sites that would produce the most energy out of these 10 PRVs. You can see that actually only 2 to 3 of them would intersect the initial investment and to have good payback periods. But it's important to highlight again that to fix the hydraulical grid, we need to install more pressure reducing valves. So it makes sense to compare the cost with the differential cost between implementing a total micro hydropower technology and its costs, or the difference between it and to install pressure reduction equipment and all its accessories. And that means that we are talking about more or less 15,000 euros, well, half of the price. So zooming in a 5-year period, the analysis that was carried out before was for a 15-year period, since it is the time that is required more or less to decrease the water losses to 15%. And zooming in a 5-year period, you can see that the investment, the payback period would be in this latter scenario 2 years, and with the initial cost 4 years. In a water supply system, however, we also did a study in the same reservoir, but this time upstream, because it's a water transmission system. And in this schematic drawing, you can see if we didn't have any regulation control, the piezometric line would be the red one. So we actually required a control valve or a micro hydropower technology device for this purpose. So we did a study and to try to optimize the equation flow times head, and we got to the conclusion that the optimal head in this scenario would be 2/3 of the different level between the upstream reservoir and the downstream reservoir. These following graphs show this correlation. So comparing the energy recovery between these systems, the water distribution and water transmission, you can see that there's a huge gap here, of course, because it's more complex to install this technology in water distribution system. Thus, it's important to first analyze it and to study it. But first, to fix the hydraulical problems within the grid, as this sentence illustrates. In order to show you how did we got to these results, in RSS we developed a software called Sherlock. Sherlock stands for Selector of Micro Hydropower Technology and its regulation, lowering the operational costs. And this software allows us to, as you can see in the picture, to choose, and this example is for a pump turbine, to choose different micro hydropower technologies and its rotational speeds, and then get the result of energy. In non-regulation mode, you would use the nominal speed, so the results would be limited, but you can compare with the electrical regulation mode, and this software allows us to study all of the rotational speeds and then to fix the optimal one in order to harness more energy, and then compared also with the variable rotational speed within the electrical regulation mode. And you can see that this last one is the one that produced the most energy, and this is for the example of the PRV location presented before that had the most potential. So the important to conclude is to never guess, because you need to first have a study, because our Sherlock never guesses. So you have first to do this study and then carry on to study the feasibility of energy recovery within these technologies.
Só para terminar em português.
Just to finish off in Portuguese, we tried in our presentation to give you a global framework of the problems and always highlight that the first step is to solve the hydraulic problem and see what we can recover, to see what we can recover, develop software for that goal. With the previous experience, everything ended up, we're trying to evolve in the sense we do not need here each person working in their own field. This has to be a global effort. We don't want dormant brains. We need the capacity to move on. We don't need to have previous thoughts like the earth is flat, etc. We don't need to be prima donnas of knowledge. I need to do something when I have everything, so I'm going to wait that everything comes down to me. No, we need to move on. In reality, what we need is to solve the hydraulic problems with teams that are multidisciplinary, with open minds to transformation and evolution. And we always need to study to see if it's worthwhile to have this energy recovery. We cannot go into wishful thinking and think that we have an iPhone with this. No, we need to study the case to see if it's worth it. To see if it's worth it not only in terms of water efficiency, but also in recovery of money. But we need to make a bit of propaganda and see some guys with nice faces in the newspapers, etc. So in reality, we need to know, analyze, project, decide, and mainly act. We cannot always think about it. Because in reality, to solve our problems, we cannot continue thinking always the same way. And that's it. Thank you very much.
Muito obrigada, Rui.
Thank you, Rui and Miguel. An excellent presentation. You helped us open our eyes to this problem. And now, the following presentation will be made by Nuno Aleixo, who has more than 20 years of experience at KSB. He has done several training sessions in Portugal and Germany. He is the head of, at KSB of this topic. Energy production, pumps as turbines, how to use them in water systems, and that's it for the time being.
The presentation in English, let's see how it runs. So I'm responsible for water and wastewater applications in KSB Portugal, and we have seen for the last few years that there is a lot of potential to recover energy in water systems, irrigation, and also in wastewater systems. We can see in this picture, in what water works, we have a lot of pipe works, water running down in rivers and so on, and there is a lot of potential to recover energy. Sometimes it is difficult to do the investment because the investment can be very expensive and even technically a bit difficult. So when we see for municipalities, sometimes they have just a small flow running on pipes. sometimes running from mountains to the water treatment plants. And sometimes they use also reduction pressure valves to cut the pressure on the entrance of the treatment plant. And this pressure means energy and could be recovered to produce electrical energy, for instance, or mechanical energy to be used for pumping water, for instance. And since KSB is a producer of, or manufacturer of pumps since long time ago, KSB developed a study to check and to test their pumps working as a turbine. Because there are some advantage to use the pump as a turbine. Let's focus first on the turbine. The turbine, it was developed exactly to work to recover energy from water. And the turbine is wide in range control. You can use a turbine in several range of flow, for instance, with high efficiency. You can use the turbine with accurate design. The turbine is designed to work with for that system and with higher efficiencies. However, if you have a low flow, short flow, and the turbine is too expensive, you can use a pump as a turbine. The pump is a standard pump, a standard product. For instance, this kind of pumps, KSB produce thousands per year. So it's a standard product with short delivery time, low price, of course, and you can use also the pump as a pump. We can see two graphics. On the right side, you have a graphic of efficiency curve of the turbine, and you see that the turbine keeps high level of efficiency near as far you go in a complete range of operation with a, let's say, wide range of operation. The pump working as a turbine, usually you can only find the best efficiency point in a certain small range of flow. So that's why the pump is not so flexible as the turbine. However, if you see that you have a potential to recover some energy in a system, and the turbine is too expensive, you should also calculate the cost and the payback using a pump as a turbine. Maybe, and probably, you will not recover so much energy, but at least you will recover some energy, and the payback could be shorter than using a turbine. Especially for small systems with small flow, and there's a lot of potential to use a pump as a turbine. Here you can see the operating range of the three pumps, the three type series pumps from KSB that could be used as a turbine. We have multi-stage pump for higher pressures, but small flow. We have single entry pumps and double entry impeller pumps for bigger flows. You can see that we can reach power until 750 kilowatts with the capacity more or less until 2,000 cubic liters per second. So you have a wide range of application for a pump as a turbine. We see some pictures of installations where we placed some pumps working as a turbine. And in this picture, we can see a pump. This is a drawing of a pump where we can see with the red arrows the machine working as a pump, and with the green arrows we see the machine working as a turbine. So it is exactly the same machine, a standard machine, usually much cheaper than a turbine, that can be used as a turbine. You see, when the pump works as a pump, the inflow, it is on the horizontal direction, but when it works as a turbine, everything works in the opposite way. We have the water coming in from top, the rotation is on the opposite direction, the shaft is connected to a motor working as a generator or even a generator, and could be another machine, a rotating machine on the other part of the shaft. And so this is as simple as it looks. We can see here the performance curves or the characteristic curves, flow and pressure of, on the right side of a pump working as a pump, and on the left side of the same machine or similar machine working as a turbine. We can see from the curve of the pump working as a turbine that the range, operating range, is not so big as it is usual for a turbine. However, with some adjustments on the system, it is possible to control the flow and the pressure to work with the pump as turbine for the indicated duty point. We also can see that for a pump working as a turbine, usually the flow for the best efficiency point is a bit higher than the flow for a pump working as a pump, and also the pressure is a little bit higher than the pressure for a pump working as a pump. We can see this picture shows a powerhouse. It was a development made by KSB to be used in some places where there is no electric grid. And it is a standard container with is the kind of the black box with the pump working as a turbine. Everything that is needed to have a pump working as a turbine, like all the pipes, the valves, the energy correctors and the variable speed equipment and so on. Everything is inside that box, and it is calculated according to the pressure and to the flow available in the place. And this energy can be used for electric grid, a small electric grid, can be used to pump water for another place, something like that. So it is, we can see in this picture, inside the container, all the equipment inside, the pump as turbine, the transformer, the frequency inverter, the valves, voltage filter, and all the pipe work inside the same container. So this is an easy way to have a pump as a turbine. Of course, it's not the solution to be used by here in Portugal by a municipality, because this was developed to send it to the jungle, to some places far from everything where there is no electric grid. But here in Portugal, or for municipalities, for water supply companies, this system can be used and made by companies like the company we saw before, where they can do the study for the perfect solution for energy recovery, and with the pump as turbine, they can build all the system around to have the system working for energy recovery. For curiosity, we have here an example of a system that it was developed in Java Island in Indonesia, in some place where there was no electrical energy. It was the need for water supply, and there was an underground river running with a very high flow, but it was about 200 meters below the soil. So KSB was a partner in this project, and they made, using 3 main pumps working as turbine, connected directly via a gear box to some pumps. The pumps working as turbine, the rotation was transmitting rotation to the small pumps, and those small pumps could pump the water to the surface. We can see here, it's easier to understand. So we see a big pump, and this pump was working as a turbine. The rotation of that pump connected to a gearbox was commanding the smaller pump that was pumping water to the surface. Of course, we had for the pump working as a turbine, we had a capacity of 370 liters per second and a head of 15 meters with a hydraulic efficiency of about 81%. The small pumps to pump water to the surface for water supply, it was a multi-stage pump, pumping each pump only 16 liters per second for a head of 190 meters with efficiency, hydraulic efficiency of 75%. So it's a nice example how to use a pump as a turbine. In this case, the turbine was not producing energy, they were transmitting the energy directly to the other pump to pump the water. Of course, there is always the need of some energy, and that's why in this picture you can see some small, a small pump. This pump was just producing enough energy to control the system for the automation and so on. And so this is a very nice example how a pump can be used as a turbine. For water supply systems, usually we have a lot of people curious about this solution, and sometimes people just think about, they made some calculations they consider a very high efficiency, they consider the using of all capacity of the pipes, all the pressure, and sometimes they are very optimistic about the payback of the investment. Then they start to ask to KSB, for instance, about how it is a pump working as turbine. As I told you, if you go out of the range of the best efficiency point of the pump as turbine, the efficiency drops a lot, and usually you have to use the pump for a certain capacity or flow and a certain pressure. And so people start to do some calculations, and they see, well, I cannot recover as much efficiency I was thinking about, and sometimes people just give up of the project because they were thinking about recovering like efficiency with a 90 or 80% efficiency, and that is not possible with the pump as turbine, because most of the time you cannot use all the flow. However, as I said when I was starting, calculations must be done, and the payback could be very interesting if you compare with investment with the turbine, because sometimes the investment with the turbine is very expensive. And you also have to think that it is better to recover some energy from a system than lose all the energy that is available on the system. There is another problem. Sometimes people from the water companies, they are afraid to compromise their main task, because they want to supply water, drinking water, and they are afraid to put some system in the middle of their system and to compromise the main task. And if you see, all the recovering system can be done with a bypass. So in case of any problem with the machines, with the recovering system, you can just close the valves, and the main system is always working. So it's not the problem for the water supply system or for irrigation system. Thank you very much.
Muito obrigada por ter cumprido o tempo e, portanto, temos uma perspectiva de poder utilizar as bombas a funcionar como turbinas. Segue-se o engenheiro Pedro Perdigão. Okay.
Perdigão.
Officer from INDAQUA. Okay, and obtained the civil engineering degree in '96, and later in 2005 he gets the MBA in Oporto Business School. Now he is member of the board of INDAQUA, a company integrated in MIA Group, I think it's the name, the correct name?
MIA,
okay,
yes.
MIA Group, that holds concessions and participations of water utilities that serves 630,000 consumers.
I'm sure Miguel will solve that problem. I apologize for this delay, but it's an interesting time to start reflecting on what we've been listening to and what is being transmitted. We need to open up this window of opportunity. We have many in the water sector, not only in terms of water supply, but also for populations and irrigation systems in the industrial part. Obviously, depending on the topography and characteristics of the systems, we have greater or fewer opportunities to implement those solutions. In terms of Madeira, for example, which has very high differences in level with problems of excess pressure in a large part of the circuit, this is a solution that we need to think about.
I just have this slide to let you know where I'm coming from. I think it's better for you to understand the example that I'm going to speak later. So I work in INDAQUA. INDAQUA is a Portuguese company owned by MIA, which is an international company that has contracts on non-revenue water projects, on efficiency in Bahamas, in Brazil, and also in America and in Spain. Okay? So what am I going to do is we heard a lot about the word smart these days. So everything is smarter since we have a smartphone. But are we smarter because we have a smartphone? I don't know. And smarter is something that we can get. Intelligenter, no. So intelligent is a characteristic we have. Smarter is ability, is something that we can develop. So I'll be talking about smart water utilities, which are kind of a person, and looking it in the non-revenue water perspective, because it's an area where it involves many departments of the company, so it's a good area to create a general motivation and to induce improvement philosophy, okay? So, starting about something that is very important whenever you want to change, it's motivation, okay? So, what does it motivate companies to reduce non-revenue water? In my opinion, it's the economy, stupid. It's the phrase that one of the advisors of Bill Clinton told him when he was deciding in which areas should he direct his campaign. So the idea is that people are motivated by economy. Believing that, what makes water utilities more motivated to reduce non-revenue water? On the right, you have the high, on the left, the lower motivation. The first one is, are the consumers paying for water losses? In many cases, it's a public entity, all the costs go to the tariffs or to the taxes, so the water losses doesn't have any impact on the company. It's all going to the consumer. In other cases, some companies earn some or lose some if they don't achieve an amount of non-revenue water. So if the water utility is partially assuming the cost of non-revenue water, the company will be more motivated. A different thing is, where is the water coming? If it's a vertical system, where you take out the water, you treat it, it doesn't have such a high economic value than when you're buying the water from a different company. So, whenever you import water from a bulk water supplier, you're probably to be more motivated to reduce non-revenue water. In some cases, those contracts have minimum consumption. And I've been in water utilities that had gone down by reducing water losses below the minimum consumption. So they were supposed to gain nothing and still pay for minimum consumption. So minimum consumption can be a motivator or non-motivator for reducing water losses. And a different thing is the high water price. So I think that water has more value than just the cost of bringing it to our homes. And the scarcity and the tendency that we're seeing should increase the value of water. So if you have higher cost of water, you have more motivated water utilities. Speaking a little bit more about this, then how can you motivate a company? An idea is measure. You cannot manage if you don't measure, but you should measure with KPIs that people understand. So Rui was talking that percentage is not a good performance indicator for non-revenue water, and I agree with him. So I put here 6 different measures for efficiency in a water utility, and they're all very confused. Efficiency is so, the percentage is so good that even journalists understand it. But it's bad to compare companies, okay? So for instance, why not use an easy indicator in the water utility that is the cost of non-revenue water? If you put that in the P&L, I'm sure that it will probably become a more urgent matter. So measure and use KPIs that people understand. Another thing very important is monitor. Monitor things, monitor hourly, monitor daily, monthly, yearly, depends. But monitor, measure, and benchmark. For instance, in INDAQUA, we have 6 companies, that's IFAF, Saint-Gobain, and all that, and they're all measured monthly on the performance indicator that we are using for non-revenue water, which is non-revenue water per kilometer of network. So monitor, put red lights, show that things are different. It's not everyone having the same results. About benchmarking, and about the percentage is a good example, you have to do it right. Not just using the right indicators, but also use a good source of data when you're comparing to others. In Portugal, our regulator has a very good source of data. There's another one called IBNet, but it's voluntarily, it's not audited, but it's worldwide. But you can have good benchmarking just using the data that our regulator puts for free, it's public. So please make sure that you're not a little bit wrong with the image that you have of yourself. So, what's the place of non-revenue water in the strategy? First of all, why should it be a goal? And you need to answer, for every goal you have, you need to answer why. So you go to your competences and to the environment, a SWOT analysis, very typical. And if you can combine a strength with an opportunity or a weakness with a threat, then you should have this non-revenue water. Maybe it doesn't need to be in the strategy map of the company, but you have to answer why. And why is very important for motivation. Then there are tools like Balance Scorecard, where you place in the map your goals, organize them, and it's a good tool to explain to people what's your strategy. And that's the place of non-revenue water in the global map of goals, in the strategy map of INDAQUA. But I like it because it interacts with many areas. For instance, we have water network renewal, or we have reduce service interruptions, or reduce bursts, and all that is related to non-revenue water. Remember that reducing bursts saves costs and increases revenues because people have water available, so they'll use it. Then, if you answer the question why, and it's a goal for the utility to reduce non-revenue water, then answer the question how. Things don't happen by chance, you need to have a plan, okay? And this is just an example of the measurement that we do, and some example of the goals. You see, every month they are rated, and according to the deviation of the real value to the prediction, they are graded. We use the Portuguese classification in the school that goes from 0 to 20 because I find it more motivating. So what's the difference between intelligent and smart? So I think water utilities are a little bit like whales. They're so big, they're so protected, they don't have to be smart. So they are thinking, and they have a huge large of thinking and analyzing ability, and sorry to say it, as Rui was saying, they waste a lot of time. I say waste, a lot of time just thinking about it. And I think they need to become smarter. And this is a smart animal. And why is it smart? Because he has good sensors, his ears, his eyes, his nose. He's very rapid thinking, and then he has the muscle on his back legs to jump and get out of there because the wolf is coming. So he needs to be smart, and he can get smarter. So if you want to get smarter, you have to have all these dimensions, okay? Sensor. Water utilities have been investing a lot in sensors, placing flow and pressure and all of that. But then someone was saying in the morning, that means big data, so you have to filter, to synthesize, to change, to transform data into information, and then you need to have analytical capacity. You need to have rapid thinking and decision. And of course, you need to have the resources, and you need to have the rapid. You need to be fast, so you need to have timely actions. So that's why we call it smart. You don't need to stop being intelligent, because that's something that you cannot. That's a characteristic. It doesn't evolve. It is born with you, so you can still be intelligent, and you should understand the concepts, but I think that water utilities need to be smarter. Okay? So let me give an example of INDAQUA. So this is using our regulator performance indicators. This is the comparison in percentage of the private operators in the country. Well, there's some public in the down, for instance, Lisbon or Porto, and they're the best in the public sector, but the private sector is much better than the public sector. So we compare ourselves with the other privates. And the blue lines are all INDAQUA companies. And we see that just one is down here, and all of them in percentage are on the top. But when you change the indicator, leaving the percentage and using non-revenue water per kilometers or per service connection, it all changes. Some of them come down, okay? For instance, even Lisbon, that has a 10.5% non-revenue water, so is much lower than the national average that is of 30, on non-revenue water per kilometer becomes with 7,000, while the national average is 2,400, so Lisbon is 3 times worse than the national average. So we did this analyze, and we thought, well, some of them, you see, are on the top, on the 3 indicators, so we believe that some of them are very good. But what happened was that INDAQUA had gone down from non-revenue water, that's non-revenue water per kilometer, until the year 2013, and for several years was stable. We had, for instance, an ILI, an infrastructure leakage index, lower than 1, and our meter error is estimated in 2.5%. So we take samples and do analysis. So what could we do? First we did was, let's see if we are looking to the right variables, to the key variables. And we were using an automatic system. We decided, it was like, stop thinking. Let's send data to that machine, and she will tell you when there's a leak, send people to search for it. And we are not understanding the process. So we went back a little bit, and we decided, let's see if we can put it on a human size, so that people really know DMAs, know them by heart. It's not just having faith on a monitor. So we did that. And we did another thing that we also talked about. We worked on the speed and quality of repairs and on the speed of the leak detection. People forget, but we can do a leak detection in many different ways, with many different supports, with good management, with good incentives, so we changed all that. So what happened is, you see the blue line is the percentage of our network that we search per year. And we went from 100 to near 300%. So we are searching 3 times the length of the network and multiplied by 3. And the black is the number of leaks that we detected and repair. So it also increased. Nowadays, what is happening is the number of leaks has stopped growing, and we're still growing on the percentage of search. So maybe we've reached a point where we should stop putting more effort in searching for leaks. I'm just finishing. So, going back to that smart thing that I was talking about, I think that INDAQUA became smarter with the work we've done. And what we did was we worked on the key variables. Okay? We also work on the resources. We improve our efficiency and effectiveness of our team, so we start finding leaks sooner, because I don't believe that we are producing leaks, we're just finding it sooner. That number must go down sometime. Okay? So that's it. Obrigado.
Muito obrigada, Pedro. Segue o próximo.
Thank you, Pedro.
He's engineering José Saldanha from Saint-Gobain Portugal. He's director. He obtains the bachelor at the University of Coimbra and the master degree as a mechanical engineering. Since 2008, he's chairman of the Portuguese National Mirror Committee for elements of piping, tubes, valves, and accessories.
Bom dia.
Good morning. I apologize, but I'm going to make my presentation in Portuguese. First, I would like to tell you a little bit about microturbines, because this is a project that we started around 2 years ago with a European partner. So we developed this project together with the European partner based on 3 fundamental ideas. One of them was the fact that we have been hearing for a long time about renewable energy. We wanted to combine that with innovation in order to find a truly innovative solution for the market and an accessible, affordable solution with an excellent revenue that could become attractive and with a service life of at least 25 years, and which could also be eligible, in the case of our country and of other European countries, to be eligible for European funds. So the idea was to use the energy available in water supply systems. That there was also an idea in our mind to allow, in some systems, especially irrigation systems, which usually are in areas of difficult access and where the electricity grid does not exist, we were constantly asked to try and get energy so that we could supply the tools, but also so that we could communicate those data to the managers of the systems. Besides that, there was also a need to develop the project with an interesting payback period so that it could be motivating, because today the economy masters our whole life. So as I said before, we wanted to have a tool allowing us to supply energy in remote places, something easy to install, so not a complex device, very simple thing. And so we had to think about the following. We all know that most water supply networks and water distribution networks use pressure-reducing valves to create a head loss, to stabilize the pressure downstream, to maintain the pressure at a constant value. And by doing that, we are wasting energy. We all know this principle. We have an upstream pressure that we want to reduce, and with such a valve, with a control valve, we are wasting energy. And often this energy, or this type of equipment, is not working under the best hydraulic conditions, or are not working within the hydraulic parameters for which they were designed. So this is the situation you can see over here. We want a head loss, but there's always the risk of cavitation, and that reduces the service life of the equipment. So we thought of going to the same places and imagining the following. We are wasting energy here, so we have to implement a solution, and this is nothing new. There have been plenty of situations that have been studied like this. We will place a micro turbine together with those valves. We will try and reduce the head loss, the delta P, that the valves had before, so that we can take a little bit more energy. We can recover a little bit more energy by using the micro turbines. So this was the principle underlying the project. The equipment itself is very simple. It has a flanged tube in carbon steel, conventional carbon steel. It has single stage or multi-stage turbines with several diffusers and rotors. And what you can see there in the cross section, well, I cannot point, but on the back you can see the turbines at the entrance of the steel tube, of the steel pipe. There is a mechanism making the connection between the turbines and the generator. The generator is inserted in this steel pipe. The water from the system, drinking water or water supply systems water, flows on the outside and helps cool the generator. It's a shielded generator, and there was also another assumption that we needed to make sure about. We know that in water supply systems there is a high risk in some boxes or chambers or confined areas. There's always the risk of flooding. And so we also had that in our minds. How could we insert micro turbines in facilities that had the risk of flooding? And so while developing this solution, we had to make it watertight. So if a flood occurred, we had to make sure that the equipment would continue operating in normal conditions and without any kind of risk. From that moment onwards, we also tried to see the range of diameters and the flow rates so that we could develop the prototypes. That's how we reached a range from DN50 to DN600 with nominal flow rates from 5 liters per second up to 600 liters per second per piece. And in this graph you can see the yield and the flow rate, and with an established delta P, we are able to have to see the total yield, hydraulic and electric. On the left-hand side, you can see a graph that you know with the flow and the pressure, and you can see the difference in height that we have in order to be able to operate with a turbine. And then we have the traditional systems with traditional turbines. When we developed the project, we thought that usually traditional turbines discharge to the atmosphere. There's energy available, and so it allows us to produce energy, and the pressure at the outlet is usually the air pressure. In the case of other equipment, like the one from KSB, they can have higher pressures, much higher pressures. And we wanted to know our place in this graph, and we reached the conclusion that micro turbines had to work with a minimum delta P of 15 meters and per piece. And we made the trials, and when I say delta P is the difference between the entry and output, the input and output pressure. The minimum had to be 15 meters and the maximum 215 meters height. And so we thought that there was an opportunity. There are systems like the one in Madeira where they have huge differences in height, where you need to move from 40 bars to 1 bar or 2. And so we thought that we needed to have a flow rate, but we also needed a device able to operate at very high pressures. So what we decided to do, and in the graph you can see that up to 0.5 cubic meters per second, it's one piece. And if we have a flow rate which is higher than that, we can associate micro turbines in parallel. So if we have delta P's within that range, okay, but if we have a higher flow rate, we associate micro turbines in parallel. If we have a case like the one of Madeira Island with significant flow rates and also high pressures, we can associate micro turbines in series and in parallel. So we can have a mixed model with two parallel micro turbines together with the control valves and two micro turbines in series. So our idea was to address this project to drinking water supply systems, raw water for irrigation, treated water, so wastewater after being treated. This was also one of our goals. And now we are performing tests with seawater. On the right-hand side, you can see a graph showing you the total efficiency. After 100 liters per second in a micro turbine of 30 kilowatts, we can reach an efficiency of 69%, a total efficiency of 69%. 100 kilowatt micro turbines can reach 72% efficiency for flow rates of around 250 liters per second. So this is one of the examples. Where can we apply this type of equipment? Traditional installations. On your left-hand side, you have the project, the diagram of a dam where you have a pipe ensuring the ecological compulsory flow. It is compulsory by law, we cannot escape it, and therefore we have there a source of constant energy because the flow rate is almost always constant with very slight variations, and so we have the right place, the optimum place to install a micro turbine which will be operating for several hours for most of the year, I'm sure. Then we have traditional water supply facilities with two reservoirs and a control valve at the arrival of the end reservoir to control the pressure or the level. So this is a typical installation. Then pressure reducing valve chambers is another possibility for the installation. This is the typical diagram of pressure reducing valve chamber. The blue is the existing installation, and in red and pink it's the part that we can build, sometimes without requiring civil construction work, and we can do the bypass and install a micro turbine. Many could say, but why do you have that ACV valve there? What is it doing there? It is ensuring the 15 meters height. So at least between the entrance and the exit of the turbine, I need to have 15 meters. In a water supply system, I have to ensure that water column. That's why I cannot have a direct thing. I have to have a pressure difference between the inlet and the outlet. I can have more than 15, but the minimum is 15. Another type of facility, another type of installation, if I have enough pressure and flow rate, I can have parallel micro turbines. To wrap up my presentation, this is a financial table that we drafted based on 7,000 hours of our working time. This means more or less 290 days. And we can see the different powers from 10 kilowatts to 300 kilowatts. We can see the installation costs, the maintenance costs. You can see the amount of energy recovered. For example, a 300 kilowatts unit produces 2.1 million kilowatts per hour. So you can now calculate the EBITDA, which after 1 year it's 108,000 euros. And therefore the payback will be in 8 years. These are just a few examples to show you the return period that you can have in each case. Thank you.
Vamos para a última apresentação.
Let's go to our last presentation.
The speaker is Engineering Margarida Pinhão. She comes from Tecnilab Portugal. He's mechanical engineering from IST, Lisboa. Has the specialization in applied thermodynamics. He's working since 2004 in Tecnilab, and he is responsible for Flucon, typical from valves. He's member of Specialized Commission of Water Distribution Systems of HAPDA, okay, and she is representative in this association of urban water systems.
Water systems,
okay.
yes. Distribution water systems.
Okay.
I have a billing presentation, but appealing to my synthesis capacity, I will speak in Portuguese. So,
I am responsible for control valves, and what I'm going to do in this short presentation will be the bridge between what my colleagues mentioned previously regarding the energy reuse and the use of control valves and the likely energy recovery to increase and improve the efficiency of water supply systems. I'm not going to repeat, according to what we have heard today, the control for water supply or production or distribution of water is the result of some interference with some mechanism that we include in the grid, whether it's control valves or to take the water to a higher height and simultaneous dissipation of energy. The control will be the result of the influence commanded by us that we wanted to put in the transport or distribution of water regarding control of valves, because it's my working field, and the presentation is in that sense. We have defined 4 main control areas, talking about the pressure control, reduction or sustaining the pressure, or any action, and as a control valve will have direct action on pressure, so the reaction will always be to create a loss of load in the grid, whether it's to control pressure, to control reservoir levels or flows. And in terms of valves, the protection valves, these are the ones used to alleviate the pressure, anticipate a loss, and anything to do with the other organs in the grid. With a 5th point over here, reusing energy. This is a measure that will contribute in a richer way to the increase of efficiency in the water grid, but it must also be measured, calculated, and assess the potential of application and payback on investment itself. The functioning principle in a basic way, I don't know if I can point over here on the screen. The lines in blue above the valve are the pilot system. In other words, the hydraulic control valve is piloted. The valve itself is the hard part, is the main body. It is deaf, dumb, and not intelligent, so it will just reproduce the behavior that the pilot defines. And now the application of pressure in the valve, when it has pressure upstream, you can see on the left, on your left, which will place water within the lid of the valve in dark blue. This is the pressure upstream and will allow water to leave or not this valve. So this will close the valve, and water coming out will cause it to open with the closed valve if the pilot is closed with the pressure reducer. In which we have a level control, when we have the maximum level defined in the reservoir, then the pilot will close. By closing, the main valve will close. If the pilot opens, the valve will open. If the pilot is measuring the variable with a proportional control, the valve will have intermediate position by maintaining the control in the grid. In this presentation, I'm going to divide the systems into two main divisions, because this has to do with the result that we can have from the action on those systems. We have the water supply and water distribution system, so different complexities, and here I'm talking about only the technical issues. In other words, pressure measurements and level measurements in a transport system is completely different from the distribution system, so I'll divide this presentation into those two fields. In the transport system, we have a water origin which is not represented over here in this schematic. This represents transport from the reducer to the storage reservoir. We have a known origin with stable conditions of pressure and the flow. We have transport to reservoir, and we have a level control in that reservoir, which is common practice in 99.9% of facilities. This is how they are working. They have a level control, and if this load is too high, it can have a pressure reducing valve or not. The conditions are stable, and here I'd like to make an analogy for the need that all bodies have of maintenance, in other words, for the stable functioning, and also the frequencies of maintenance. We need stable functioning conditions will cause less problems in terms of longevity and the life of the equipment. So in terms of energy reuse, we will have a loss of load which is necessary to maintain the system in security and safety, and in case we need to have energy reuse with pumps and pumps working as turbines, whatever, we need to take advantage and reuse that energy that we're dissipating through the valve. From the studies already carried out and mentioned earlier, the potential. Here we have a potential energy that is totally available and non-variable. The potential of investment and payback on this investment will be optimized in a situation like this, in which the conditions are stable and the available load is always the same without many great variations. Either we have water all in movement or totally stopped. So that would be the ideal situation, as we've already heard before. And regarding the control valves, the practice that we recommend as good practice, the ideal is to have the installation with reduction valve and bypass. In case we needed to have maintenance to reducer, we don't need to interrupt the water supply if we need access to the turbine because of a stoppage or because we have limitations. and barriers that can be placed regarding the equipment functioning, or have an excess or lack, or because something happened in the grid that prevents us from having the best efficiency. The bypass is always the ideal to be dependent, not to be dependent on only one line, so that we can avoid these problems. Talking a little bit about the valves to be used in this kind of facility, we have the simple reducers or with remote control. I'm talking about the hydraulic question more, because what we can do, we have electrical supply, we can change these variables that we need or that we wanted to control. We can have a reducing pressure working. If we have a remote control, we can control it with flows, levels, whatever. We have sensors in the installation that we can control the way we see fit. When we don't have this electrical supply, we have to fall on the hydraulic, and if electrical energy is cut out, this ensures the functioning of the equipment and its protection. Hydraulic, since we have flow and pressure, is always ready to work. The reducer can be simple or with remote control. Controlling the level will work the same way. We can have hydraulic control or electrical controls that can allow us to manage the variables or the system according to our needs. Going to water distribution systems, the issue is a little bit more complex, even for pressure control or management. Here, let me call your attention to the pressure management and the efficiency of the water distribution systems, because a management of the pressure that is more efficient will be the one that is adapted to the profiles of consumption in the grid. The grids can be somewhat complex, slightly complex or very complex, depending on the way they are built, because this is common to all cities on all corners of the country. Cities grew, and the networks were not dimensioned right from the beginning for the needs of population growth or the territorial extension of these villages. So they were always added on, and this is a problem that is a problem for all companies, be they private or public. In terms of the pressure management, from the point of view of the definition of the valve, which is ideal for the installation with energy reuse, makes this issue a bit more complex. The available energy to potential reuse is variable now, as we've already mentioned, I think by Engineer Saldana, in terms of the over or under dimension. And talking about valves, they have to be sized correctly for the flows. In case of fire, which is something which is an aggravation, they have to comply with peaks of fires that we hope are never necessary, but they have to be foreseen. Those who have water supplies, some of those present here, know the problem of the ideal situation being the whole main installation of the bypass, not only for maintenance, but also maybe to place ideally different sized valves so that the nominal and real flow can work within a smaller valve within the ideal standards of consumption. And in the peak we have another relief valve. That would be the ideal situation, and in reality that's not always possible because of different issues. And because of the experience that I have already 14 years working on this, I think this has a lot to do with not only with the cost itself of the installation, but the lack of provision for that cost. I didn't give you this example here, but in a valve box of 80 millimeters, for example, in which you have a pressure reducer, in which we foresee the construction of a new valve box in the city center, in which to open up a space for a box, some paths with or without bypasses. The difference for an investment, for example, of 10,000 euros will be another 1,000. So in the beginning of a work, this is absolutely irrelevant in terms of this addition. And I'd just like to leave you with this idea, because it seems irrelevant, but to make this question of having the reducer using bypass with turbines or with another reducer, whatever other way, if it really exists, it makes everything simpler. If it doesn't exist, it might imply a new work. So it can place us in the field of moving on, or on the other hand, not being able to do so. Regarding the issue of pressure and pressure management, what we want in a distribution grid, maintain this value as low as possible, which meets the needs of the grid, but does not place too much pressure on the grid. They have distinct capacities and functions. Leakages exist. We cannot eliminate all of them. If we maintain pressure in the lowest possible pressure to satisfy all consumers, we for sure can have less water that is being lost in the places we're already losing some. Regarding amplitudes, the lower the variation that we are able to get an amplitude of pressures within the grid, the lower the stress that we cause in the pipes, so the lower frequency of leakages that we will have. And now let me move on to the final part of this presentation, which has to do with the pressure management models. Okay, now let me speed up a little bit. I had left this out, but I'll put it back here again for a simple reason. The efficiency of the application of a simple reducer in a grid where pressure is not being controlled or minimized has more impact very often than placing a super valve with super control with measures of pressure in critical point and the automaton than placing a simple pressure reducer. I think you mentioned this in your presentation in the case of Cascais, where you had this bypass. Sometimes we oversee 1 bar, 1.5, or even half a bar can make all the difference depending on the characteristics of the grid. That's why I think, and I share this opinion from my colleagues, it's important to know, measure, analyze, and take the steps after the analysis. In terms of the sophistication of the solution, it can also allow us to have a result in efficiency and a reduction of leakages and losses, which is proportional. We can use in the grid models of remote control of these valves through the measurement of pressure and the flow. Here we can have support from electrical supply. The reducer can be a standalone and completely self-sufficient. If we want modulation per consumption to adapt 24 hours a day to the characteristics of consumption, we have to have instruments. We have to have pressure measurement and flow measurement and automaton of controlling the valve, and all these need to be supplied. If in this, if you can have energy reuse that can also supply these instruments, that will be the ideal condition. And to end off, we have the maximum optimization will be remote node modulation. We have pressure measurement in the grid where the pressure is at its lowest, and we have the transmission of its value for the control valve or the automaton that will control the control valve. Difficulties in applying this, it's the most sophisticated solution. It's the one that allows us to have the best results, but it's the most complex to install, because to know the critical point and to be in a point that is easily measured, we need pressure measurements from this place to the place where we have the valve or other instruments. It has to be very well assessed, and we need to evaluate the costs of implementing this. And here I'd like to end off this presentation by making the analogy in the distribution grids. If you have the possibility of having energy reuse, we need to measure the conditions of applying it, because we can have characteristics or needs for pressure and flow that will not allow us to put the equipment in the correct and ideal place, and that will lead to investment that will not have payback in the time that we would see it as ideal. So the application for control valves, like any other form that will contribute to the energy efficiency, we should take a look at these conditions. Thank you very much for your attention. Thank you.
Kemi, Dr. Kemi, can you help me?
Dr. Cumming, could you please help me?
Todos nós aqui presentes.
Let me explain to you. We have all heard these presentations, but we now will see 7 questions. On the left-hand side in English and on the right side in Portuguese. If you do not have these devices, please pick them up over there and for you to vote in each question in order to give us your answer, and you have 30 seconds to do that.
Okay, you can vote the first one. Is it counting? Yeah. Passem para lá. Stop. Please pass there. I think it's easier. Okay. Podem. Sim. Rápido. Okay. This is the. No. It's now. It's not copy. This is the first one. Okay, this is the first question. Please read in English or in Portuguese and let's try to answer. Nove segundos. 8, 7. Okay. The second question, you can read in English and podem ler logo a seguir em português.
You can read in English or in Portuguese.
Para quem ainda não tinha votado.
For those who hadn't voted yet, you still have some time.
Double vote here. Estamos duas vezes. Yes. Okay. Pergunta 3.
Third question. Can you read it? We have 25 answers, but we need more.
Just count down. Just count down, okay? This is our reality show, okay? Let's see who is the best. I think it's Rui. Okay. Next one. Next one, okay. Pergunta número 4.
Question number 4. Here you can choose 3 answers, up to 3 answers.
Select 3 options. Since we have 3 options to select. We have a little more time, okay? Uma vez que temos 3 respostas a dar, começamos a contar um bocadinho mais tarde para poder dar tempo. Ok? Ok. Pergunta número 5.
Question number 5. And here you can choose again 3 options.
Estamos a dar um pouco mais tempo para...
We're giving you a little bit more time for you to vote.
select the 3 questions, 3 answers. I think we can. A partir de agora, temos só 25 segundos.
25 seconds from now.
This type of results. She was elected Miss Portugal. Só temos mais 2 questões.
2 questions left. Here you have to rank 1 as highest and 3 lowest.
Point, okay, the highest classification, 2 medium and 3 lowest. Okay, we can count down. Ten seconds. Okay, and now we have the last question. And the same type of vote, 1 for the highest point, okay, that you consider most important, 2 medium and 3 for the lowest. Okay, o ponto que consideram mais relevante.
1 for the highest and 3 for the lowest importance.
Okay, this is the countdown. Kemi, we start later, okay? So, it is not bad. I made 2 minutes. You agree? Okay, since we have no much time, I'd like to make a summarized summarize. After this summarize, we can make 2 or 3 questions to close the section. Okay. In terms of summarize, I'd like to announce. I will talk in English now. I would like to announce that the importance of water industry in the Atlantic area, since it is the most energy intensive consumer. And of course, through the REDAWN presented by Dr. John Gallagher, the energy efficiency is very important for all types of water networks, not only for drinking systems, but also for irrigation and process industry. Since we have water flowing in our pipe systems, even can be applied, of course, in open channel flows for irrigation systems. We have to adapt our machine for these situations too. A second point, it was about the scarcity of water and increasing of water demand. It is more and more required new efficiency and effectiveness solutions. As mentioned by Rui Silva Santos through his company, he is developing a very interesting study, and he is open to analyze other systems from other municipality systems in order to evaluate the possibility to make recoverable energy in the pipe systems. And of course, this is important since it connects the water energy nexus, and this is the main factor for the near future. In terms of the solutions from KSB, the engineer Nuno Aleixo presented the PET technology. Different configurations can be obtained, the comparison between a pump and a pump working as a turbine in the reverse mode. In the fourth point, it is about some key factors about the success in water loss reduction, presented by INDAQUA, engineer Pedro Perdigão. Since the motivation to change is important, it's very important, and definition of best strategy to obtain good performance indicators. And if you have these good performance indicators, of course, this will affect the overall performance system. The next point, it was about an overview of a new microturbine. I heard about this when I was in SMPGA in Normandy, in France, and it was great to bring also here the solution presented by the Pont-à-Mousson, Saint-Gobain, através da representação portuguesa, through the Portuguese representation here. We have a compact microturbine adapted for different situations, for high and low pressures. It is quite versatile and can be used in the water sector. At the last, not the least, okay, the control valves and the potential energy recovery are quite important in terms of the efficiency of water systems. This conference is about water efficiency. It is, of course, correlated with several types of valves that we need to install in our water networks to control the pressure, to control the flow, and why not to incorporate also some microturbine in this type of valves. Okay, we can try to integrate the different solutions that some years ago we thought in different parts. Okay, individualizing the different components. Nowadays, we can integrate this and optimize our solution. I would like to thank all the speakers, and the audience. Somebody comes from Madeira. It's very important to enhance the interest on this subject. Okay, to finalize, I would like to ask 1 or 2 questions to the experts. We have not much time, but we can discuss, if you are interested, to discuss the industry that come here, and all the experts are invited for the lunch. And we can discuss some issues, some aspects during the lunch time. We have to fill the schedule, okay, of this conference, so we have no much time. If you have one or two questions, no? If not, yeah, okay.
We're sorry, but we have no sound from the audience in the booth.
Gabriela, you need the microphone in order to translate this, okay?
Muito boa tarde.
Good afternoon. I would like to know if, regarding the REDAWN, the irrigation project on the left bank of the Godania River, which is in a project phase, it hasn't started yet, if we shouldn't have an action with IDM and the project being carried out in the sense of integrating this equipment to increase the efficiency of the grid, which in this case it will be the primary grid, and then it will become the secondary grid. It's one of the places where I think we would have a greater yield since it hasn't been built yet, because after the grid has been built, whether it's distribution, that I know several distribution grids in Portugal, it's very complicated because it becomes highly expensive. Nevertheless, there are places where this could be researched and integrated. Thank you. I don't know if anybody present can answer. Yes, engineer? Well, answering specifically in terms of micro turbines, we have already made a presentation to the ADA board and its technicians in the sense of giving them all the knowledge, all the technical details of this solution of energy production. We can say that the presentation that we did at ADM to all the technical staff and all the collaborators of IDEA from the technical area, be it from the engineering or maintenance, and we also presented to the board a more complete presentation. So today we had 15 minutes. We had to just skim the surface. But at IDEA we had a full presentation on this solution. Well, now regarding other facilities and equipment, of course my colleagues can answer that. I'd like to ask you to be brief because of time, because at 1 o'clock we have another session. From KSB we have a solution for some, we have a collaboration with ADM because of the turbines. ADM knows our product very well and solutions, not only as pumps as turbines, but also the turbines for this application. I have a slight idea that from ADM, one of the issues placed, they usually need the pumps for pressure for the irrigation grid, and they don't have so much need for the reuse or the reduction of that pressure. I think there's another question. Well, they can have some interest in this. They can answer for themselves. For a point here, those projects, namely on the left bank of the Guadiana, those projects have already been done and are ready to be launched. It's somewhat difficult, I think, for them to be able to change them, but it is undoubtedly a question with potential, and just like in many other entities, I think we have the need for them to see something working, to have as an example, and start thinking more seriously on that application. But it's an interesting idea, And by the looks of it, Saint-Gobain has already spoken about this. We've already mentioned this, and we are pushing things towards that so that we can open up people's minds. It's a question that is relatively new, and there's some fear in starting here, even in terms of people who make the projects, to get themselves committed regarding the main goal. But we are betting on that to see if we can reach that. So we've already understood there's a change in paradigm. So we are thinking about only in energy use for pumping, but now we also think about hydro production, even at a small scale. So I'd like to one more question. Okay. Well, you said 2. Okay, so now there are 2. I'm Tom Carrillo. I'm a VP of the Sozelo City Hall in Alentejo, and we're here with pleasure to see if we can learn something with everybody here. And I'd like to mention the lack of fundamental play for this project, which is nowadays it doesn't make any sense to have a project without include this technology. So the absence of those players is something lacking in the organization. I apologize for mentioning this, but now my question for the engineers, which is as follows. If you have an idea, any notion of the percentage of the energy recovery versus the energy used in a distribution grid. I'm talking about a distribution project of distribution of water to a population. Rui, maybe you can help. Thank you. This is difficult to cover everything and meet all the interests. So we try to bring as much as we were able to. Is this working? Well, the question is, well, as we've already mentioned previously, we cannot generalize this, including in the situation that we saw in Madeira, which is an average inclination of 23.5%, which is much higher than that of our Alentejo. But even there, it's very complicated not to have to choose only between a very limited area. The example we gave previously, in the pilot area in Funchal, we are creating 50 new levels, and they only have potential for that recovery in terms of distribution network in terms of 3, since we have very high flows and a lot of inclination. So in my opinion, it's not possible to say what we are able to get or not generally in a generalized way. We have to do this case by case. An example that we gave in Madeira, when you have the possibility of these 3, we also have a high potential in the areas of low consumption, which is in terms of the distribution in supply. But usually these are not the city halls that take decisions, or other companies. And for the reservoir controls, there I think we have a lot of potential in the areas of low consumption. It's very difficult to have many facilities that can have that recovery in areas with great flows and differences in heights. That's possible. As I say, I don't see it possible to generalize in terms of number, but this is really case by case, as all my colleagues showed regarding micro turbines.